So let's get started. So today, I'm Carlos from Linaro. Today we're going to be talking about using LLMs in our CI loops. So before I start actually talking about LLMs, let's take a look at the current CI. So there are basically two ways of investigating regressions. You can either do that manually by checking the regression yourself, doing the bisection, and then reversing the patch or notifying the author, or you can do automated stuff like Linaro does. So whenever a build fails, a bisection is triggered, and then the author is notified by email. The problem we have with this is that these things are very time-consuming. Sometimes takes hours to do this, especially when building the compilers. So we're thinking about how can we bring this time down. So that is the motivation for this idea. So can we use AI to optimize this process, more specifically LLMs? So why? First, it is known that LLMs are perform very well in contained environments, and software projects are very well-contained environments, just as source 3. And the other fact is that these new models are very good at reasoning, so they can provide fairly good analysis if you provide the correct prompt. So the idea is instead of triggering the bisection, running the bisection that takes minutes to hours, why not we just skip the bisection altogether and ask the LLM to identify the commit from the logs for the failing logs. And that would bring the time down to seconds. Problem. So for running LLMs, you know that if you run on premises, the requirements are very high, like both hardware and energy. If you're calling the APIs from the cloud, that can get very expensive, depending on how much you're calling the APIs. You also may get some latency and availability issues. Today there are too many models to choose from, and not all of them excel at coding, so we need to choose carefully. The accuracy of what you get from an LLM depends on how well you prompt, so you're basically limited by your ability of writing. And there's also the data privacy issues with third-party LLMs. We don't actually know what they're doing with our data, so that's a concern. With that, our goal should be maximize the accuracy of this process while minimizing the costs. And by accuracy, I mean finding the correct culprit commit for each failure. And we should be leaking any private data. We should be taking any unnecessary copyright risks. So with that, we can roll out running LLMs on-premise, because that's very expensive. We have to run the cloud, but even running in the cloud, we need to be careful about how the cost of calling the model APIs scale. When we choose the model, we need to choose something that is very good at coding, and that requires no training, because training is also very expensive. When it comes to the prompt, we need to be careful to ask the right question and send only the necessary data and constrain the output that your model will spit out for you, because these things are charged by input and output token counts. And finally, we should be using only public data, and we shouldn't be submitting any code to avoid any copyright concerns. So with that, we have set our scenario for creating a small proof of concept to see if that works or not. And the proof of concept is very simple. So we chose the LLVM buildbots as an example, mainly because that addresses most of the data concerns. The LLVM buildbot already has a public REST API, so we can fetch all the data from the buildbots using that API. So we are only using public data. We'll be running this on AWS because the pricing is very competitive, I would say very low. Their inferencing is distributed, so we don't have any latency and availability issues. And it's very easy to deploy like web applications, and that costs very low. For the model, we will be using Anthropic's Claude 3.5 Sonnet, mostly because it was pre-trained on LLVM, so we don't need to train anything. And it doesn't have access to the internet. I'm aware that's a new version now that does, but when we did this, it was offline. For the prompt, we'll basically ask what is the culprit commit for that failure. We will be sending a pre-processed version of the logs just with the required data and the list of changes. And we will ask the model to constrain the output to just the commit and a small analysis. So with that, we are not using any LLVM code. We're not submitting any patches to the model. And the model doesn't have internet access, so we address all the concerns we had before. And this is actually implemented as just a couple scripts. So one that will fetch the data from the buildbot, the other that will use that data to call the model and get the response. So when we fetch the data from the buildbot, we'll be getting the failed steps, the failure logs, and the change log between a good build and the bad build. For the failure logs, we are pre-processing it, removing everything that's irrelevant. So it's basically the error message that remains. On the LLM side, the prompt should be structured like the way that's canonically done, like a question, the context, and how the output format should be. So the question will be obviously what commit caused the failure. The context will be the files that we sending that we fetched from the buildbot. And the output format should be just the commit, the patch author, and a very brief analysis of why it chose that commit. So if we run these two scripts, we'll see something like this. So we run the first script that fetched the data, then we just call the second one that gets that data and sends it to the model. So here we can see that it identified the commit for this particular failure. It has a very brief analysis of why it identified that failure. And from our tests, this has been running for like 2-3 months maybe. It's about 90% accurate whenever it can pinpoint a commit. Sometimes it can't find a commit because either the logs are malformed or some other reason. And when that happens, sometimes it hallucinates, so it's the performance is not that great. But as you can see, it's working. Like it can identify a commit that caused a failure. So now that it works, we can just integrate on what we currently have. And for that, we need a web application. So we need something that monitors the buildbot at regular intervals. We need to call the model whenever a failure is detected. And we need a dashboard so we engineers can monitor the actual status of the buildbots. And the application looks like this. So it's a very simple web application. So there is one function that calls every 15 minutes. That function basically implements the two scripts that we did on the proof of concept. The only difference here is that we are actually getting all the buildbot status, not only the failures, because we want to monitor the whole status of the buildbots. And we are writing things to a database instead of disk. So that's mainly the only two difference from the POC. On the UI side, you have a dashboard where we can monitor the status of the buildbots. That dashboard is fed by an API that will fetch the data that we wrote to the database and populate the dashboard. So it's a very simple web application. And it looks something like this. So if you open the dashboard on your browser, you'll see a screen like this that shows you the builders and the current status. So if it's green, it's going to show you the last failure. If it's red, it's going to show you when the last was less successful. And whenever there's a failure, you can click on the build number, and you'll see a model like this that will show you the relevant buildbot data. So to even point you back to the buildbots in case you want to inspect the raw data. To show the failed steps, and if you scroll down, you'll see something like this, which is exactly the same we got in the terminal when we're in the scripts, but now in a web page. And the commit will link back to the LLVM GitHub repository. So it's been working fairly well, and it's been used for us at the toolchain team to help us monitor the LLVM build bots. And that concludes the experiment. So what we learned from this. First, we learned that we can use LLMs. They are quite useful if you know how to use them. It actually can save us a lot of time when we analyze failures for a very low cost. We learned that we don't need to provide a lot of data because since it was pre-trained on LLVM, we need to send very limited data so it can find the commits. So we are running about 5,000 input tokens, 200 output tokens. A token for Anthropic is about 4 English words, so that's a very low amount of data. On the bad side, this experiment only works because it was pre-trained on LLVM, so if your source tree wasn't read at any time by Anthropic, then you can't use it. Probably need to either train your model, use another one. We learned that the prompt influences the accuracy a lot, but because when we started this, it was very inaccurate. And I think here's the golden thing about this kind of project, that we need to fine-tune the prompt to get things correctly. And if you're not careful, your costs scale very, very quickly, so it might get expensive. But the most important lessons are these two. So these things are like statistical. They are to be trusted all the time. So you always have to have a skilled engineer to double check the results, because these things do hallucinate. Sometimes it's like points to a completely wrong commits, but experienced engineer can either see, oh, that's correct or that's wrong. And most important, so this is a tool, not a replacement for real engineers, real like good engineers. So when used correctly, it can improve our work a lot. If not, then might actually get in the way. You may be asking about how can I see this working, and where can I see this? So we will have a demo on Friday. This is actually online and now. You can check the URL yourselves if you want to. I can give you that to you, but we will be running a demo on Friday, so you can test the dashboard for yourselves, inspect failures, and take a look at how the LLVM build bots are being monitored using this tool. And that's all that I had. Thanks. Questions?
How did you find out that Anthropic was trained on LLVM? Was that just poor guesswork, or? Yeah. Okay. Cool.
Yeah. So actually, it's trained a lot of things. Like pretty much everything that's online, it's working.
Yeah, thanks for the talk. Couple of questions. What is the strategy that you're using to find error in the logs that you're feeding to your LLM? You mentioned that you're finding the errors.
Okay, so to find the actual errors, so Yeah, LLVM actually has a very standard way of showing the errors. So you can just look for the error header. Sometimes if it's a build error, then it's another function that does that. So it looks like for make errors, stuff like that. So it depends actually on what you can find. So the first match, it's what it takes. Yeah.
So what's the size of the build data that you are feeding to your LLM? Do you have any size estimates? Is the data being fed from multiple builds to the same LLM inferencing instance?
What do you mean by size?
How many tokens or
Very, very few. So it's about 5,000 tokens. The hard limit for Anthropic, I think, is 13 kilobytes of text, but we are using less than 8. Okay. Yep.
So you said that the input is the error message, the build log failure, and the change log. And you said you're not sending any patches to the LLM, so you're sending the failure log and the commit messages from.
Each patch that's between the builds.
So you have a baseline to select.
The baseline is always the last.
Okay.
And git log, I believe, includes files changed.
Git log doesn't, but the buildbot does. So you can get that. Another question?
Yeah, just last. Did you consider using a RAG system which tries to extract the context of, like from your build log, why to field the whole build log and change log everything to the LLM? Is there a reason why you are doing that?
The change log. Well, we need to find the change log in particular because it's because of the list of files. So since I'm not seeing the patches, the model needs to infer from somewhere what changed. So it's the commit message and the list of files. That's why we are saying both. Yeah.
Out of curiosity, in those 10% cases where it fails, and it's not because of mangled logs or something like that, has the system ever experienced any hallucination, pointed it to a commit that didn't exist, or a test case, something like that?
Commit that doesn't exist, no. Mostly because the way of we wrote the prompt. But sometimes, let's say you have either a build failure that's the error message is not very clear or something like that. Then sometimes it either can tell you, oh, I couldn't find commits because of this, because the data is incomplete, or sometimes it, invent something out of the blue. Yeah. Okay.
Yeah, you mentioned that the prompt was important to go from 50% to 90%. So I was wondering what kind of improvements, what was the most important thing to fine-tune your prompts?
For this particular case, it's the context of the prompt. So after you ask the question, you have to contextualize for the model what you are looking for. So I had to experience with how much data I actually needed to send. So I started with very little, then was failing a lot. Then I sent a lot of data, and it was very expensive. So it was basically like a binary search of how much information I needed to send. And then at the final version, it's just the change logs and the error messages.
Okay, thanks.
Did you guys do any estimates on what it would cost to train on a private code base? And it was already trained on LLVM, which I guess it was a big boost. But if you guys had like any cost estimate.
I didn't, but we can do that because the prices, at least for AWS, Bedrock, they are public, so you can look at the how much it costs to train the model. So you can just infer by like how big is our code base and versus how much costs per token. Yeah.
So you asked for an explanation of the failure as well, right?
Yeah.
Was that useful at all?
Actually, yes. I can go back here. Here. So there is a small analysis on why it shows that.
So a follow-up, like being an LLM skeptic, right?
Yeah.
Having looked at, we also run an LLVM CI, and most of the time, the failures are, like Maxime said, in the code that is touched by the commit, right? Like so, if there is a match between the git commits, like file or the new test added, and the one in the error log, then it's a simple heuristic, right? So how much value is there in running LLVM or a base heuristic?
Sometimes, so yeah, that's true. But there were some times that it identified a commit that we were almost sure that wasn't that, but then we read the explanation and that might be a good idea to test that, and then we verified that that's correct. So for the obvious cases, I agree with you. It's like maybe a waste of money, but for cases where you are dealing with patches that interfere with other areas of the compiler, it's very much more useful.
Yeah, and it definitely gets more use when you have more complicated scenarios where, then you build your source code and then that fails, right? At that point, you want to bisect. There, it has like an LLM can have more value.
Mm-hmm.
I agree.
Yep.
So basically, I wanted to add. I think there are sometimes a number of commits in a particular failure, and when you have to scroll through all those commits, it makes your life easier. You just don't have to go through all the commits, even if you can just look at it and you can find it. But LLM makes your life easier by just giving you that commit on the spot instead of you going all the way through all the commits.
And we are out of time, so please continue this discussion at the demo Friday.
Okay, thanks.